Hello. Welcome to our paper, Content-Aware Image Color Editing with Auxiliary Color Restoration Tasks. In this work, we investigate the task of diversified image color editing. Its goal is to edit an image's color tones into diverse styles, while the content and structure is preserved. Illustrated in the pipeline figure, the input typically comprises a raw image and random noise as the style latent, leading the model to generate edited images with a spectrum of new color tones. The dataset typically consists of one-to-one pairs of raw and target images, challenging the model to learn one-to-many mappings from these pairs. Prior methodologies have limitations. In color editing tasks, non-expert users often seek automatic and intelligent batch tuning. Existing methods depend on specific instructions. Without them, outcomes become random in style and quality. Previous methods consistently produce the same color style for all input images, limiting adaptability to content and semantics. GAN-based methods lack robust modulation of input condition images on editing style, as the connection to integrate features with the original style latent is not enforced due to indirect discriminator loss. A third limitation involves the variation of appealing color tones within different semantic regions of a single image, such as foreground and background. GAN-based methods, in contrast, typically utilize a 1D noise vector as the style latent, resulting in a global color style applied to the entire frame. Consequently, our proposed method is structured around two primary aspects. In the first aspect, we leverage diffusion models to enhance the model's capabilities. These models incorporate spatial latent noise, matching the input image's shape, and are concatenated with spatial alignment during the denoising process. Additionally, the reconstruction loss aids the model in capturing precise aesthetic editing styles, going beyond the production of merely natural outputs. The second aspect involves the introduction of several auxiliary color restoration tasks, jointly trained with our main color editing task. These tasks encompass colorization, addressing luminance to chrominance completion, and its counterpart, chrominance to luminance completion. Colorization tasks assign colors to grayscale images, crucially dependent on input semantics. Inspired by this, we integrate colorization with our core editing task, compelling our model to prioritize input semantics and refine nuanced editing styles. Colorization outcomes reveal a spectrum of predicted colors for diverse elements like walls, trees, skies, humans, and cameras. Joint training enhances our model's ability to produce content-adaptive colors, showcasing a heightened understanding of input semantics. Addressing colorization limitations, we introduce a complementary task, chrominance to luminance completion. Seamlessly integrated into joint training, this task enables our model to predict reasonable brightness for specific input scenarios. Luminance completion results exhibit significant differences in ideal lighting across scenarios. Leveraging this variability, our model excels in generating diversified, content-adaptive brightness. Presenting our key image color editing outcomes, our model adeptly generates appealing outputs without human instructions. Using random noise inputs as style latents, it tailors editing color styles to input content. In contrast, space edit ventures into hyperbolic colors, jeopardizing quality and harmony, resulting in pronounced artifacts and incongruities, especially in dark foregrounds and dyed white clothing. This comparison highlights our model's content-aware color editing across diverse patches from the same image. Each row's first column features input images cropped from the original, showcasing varying locations and semantics. Despite using the same style latent Z, our model dynamically adjusts color tones for different elements, such as deepening for the sky, becoming subtler for the building, and delivering clear, warm tones for human skin. This demonstrates a consistent major color editing direction. In this illustration, we contrast two distinct scenarios, an outdoor far landscape and an indoor close object. Both Space Edit and our model transform the sky image into exceptionally artistic colors. Applying the same style latent to the clay pot image, Space Edit, lacking adaptation, distorts the object unnaturally and unfavorably. In contrast, our model adeptly preserves the reasonable scene and object, enhancing them by introducing varied lighting and shadowing in the specified colors. This table provides the quantitative outcomes of our methodologies across various configurations of auxiliary tasks, baseline vanilla diffusion models, and prior works. Our models consistently surpass state-of-the-art methods in both generative fidelity and diversity. The following table illustrates the outcomes of our user study. We presented each user with 2 sets of 16 edited images generated by SpaceEdit and our model using random noise. Our model consistently produces superior color editing outcomes across random samples, ensuring aesthetic and appealing results without the need for human instructions or post-selection. We conducted ablation studies on our auxiliary color restoration tasks, intentionally reducing input color information to prioritize semantics and structure. Simulating this through straightforward perturbations in raw input images, we found that this naive data augmentation causes mode collapse, compromising output diversity. Our model effortlessly extends to diverse downstream applications, recovering style latent noise by reversing the denoising process. This noise can be applied to other input images, enabling seamless transfer of the editing style. Results show our model accurately extracts and adapts the desired color editing style compared to other methods when transferring the same reference style. Our model excels in open vocabulary language-guided image color editing, utilizing the clip-guided diffusion inference process without the need for training with text captions specifying the color editing style. Benefited from our auxiliary tasks, our edited colors exhibit heightened realism and adaptability to specific environments, encompassing both luminance and chrominance considerations. Furthermore, for gauging the correlation between the output editing style and input image content in generic image-to-image translation tasks, we introduce a novel set of metrics named Content Awareness Metrics, or CAM. Traditional diversity metrics assess the variety of output editing styles for a single input image and multiple style latents. As a complement, we propose to measure the relationship between output editing styles and input image content across numerous input images with a fixed style latent. The fundamental CAM1 computes the mean pairwise distance among output editing styles. A notably large value implies a lack of control and interpretability in the model, while an exceptionally small value suggests that the output editing style is entirely dictated by the style latent, with no adaptability to input image content. To account for input image content, CAM2 calculates the correlation between pairwise distances among the input image's content and pairwise distances among output editing styles. Expanding to involve more random style latents for robust results, CAM3 further computes the correlation between pairwise distances among input images content and pairwise distances among distributions of output editing styles, considering multiple input images and multiple style latents. We perform both validation experiments and model comparison experiments on our proposed content awareness metrics. In the validation phase, we intentionally introduce random noise of varying scales to the raw or target images. The outcomes validate that our metrics align well with these synthetic data manipulations. In the model comparison phase, our model outperforms other baselines, achieving the best values across all 3 CAM categories. Thank you for tuning into our video. For in-depth information, please refer to our full paper.